Thank you for having us. Before Lucas starts with the main topic of today's presentation, I will give you a short introduction and explain what motivated us to use machine learning. Yeah. Better? Yeah. Okay, great. So I will give you a short introduction and explain what motivated us to look into machine learning algorithms to interpolate combine harvester yield data. Lucas and I work for the Department of Agriculture at the University of Applied Science Kiel, and as you may know, farms are pretty much gold mines when it comes to geodata. Modern farm equipment like tractors and combine harvesters basically generate a lot of geodata, just storing every second data about all operating conditions. This includes parameters like fuel consumption, speed, crop moisture, and yield. Also, the temperature in the driver's cab could be recorded if wanted. And additionally, they can be stored together with GNSS position. And basically, every sensor reading that is going through the Canvas system of such machine can be stored that way. So we have a high potential in this data. And additionally, we have a lot of different other data sources like drone images, satellite data, soil maps, and digital terrain models that are relevant to agriculture. So the potential is very big, and it is being more and more utilized, but still only a small proportion of this data is actually used despite many possible use cases. And one of these use cases is working towards solving one of the biggest challenges in modern agriculture, balancing crop production with climate and environmental protection. And to help with this, farmers can participate in annually funded climate and environmental protection measures, such called as eco-schemes. They are part of the European Union's Common Agriculture Policy. So farmers can take part of their land out of production or sow flowering strips as habitats for insects and wildlife, and in return they receive compensation payments. So the farmers has to decide each year which eco-schemes they can implement on their farm and where to implement them without financial disadvantages. Normally farmers draw such decision based on their extensive knowledge in managing their fields and also on field level assessments. But if we look closely at farmland, we see that production conditions can vary in small areas. So field scale evaluation of data might not be enough or sufficient to identify all zones in a field that are beneficial to implement eco-schemes. So site-specific analysis of production data is necessary to support this decision-making process. So Lucas and I were asked to make or create a proof of concept for a web-based decision support system for farmers, which we actually recently completed. And during this proof of concept phase, we focused on analyzing yield data recorded by combine harvesters to evaluate field productivity. And the main requirements for this web app were an easy-to-use web interface, automated data processing, and automated parameterization of these methods. So the goal is basically that the farmer just needs to upload his field boundaries and his yield data sets, and all the data processing is done by this app, and he receives in return a report containing a map which highlights zones where the implementation of eco-schemes is recommended. And if we look at the structure of our web interface, we see three main modules for data processing. The first one is the pre-processing step, which is basically cleaning the raw data that comes from the combine harvester. Then the interpolation module, which is our main topic today, which turns these point data into continuous yield maps, which are then the basis for the economic evaluation of these data to identify the zones where ecoschemes would be beneficial for the farmer. Yep.
Okay. So, I hope that works. Yeah, great to be here. Actually, last year I was attending to GeoPython, and there my journey began with geodata actually. So before that, geodata was something like a little mystery to me, and it was more headache than fun. But GeoPython taught me a different way to look at it. And yeah, the main thing what I was interested in last year was the interpolation method, so geospatial interpolation. And so to find a method which needs or fits all our needs was done by, we conducted a study to do that and make a model comparison. To give this somehow a bit scientifically robust framework, I did my master thesis in this field, and we also presented our results earlier this year at the GeoTagung, which is the Gesellschaft for Informatics and Agriculture. So, like I said, we made a model comparison, and I want to give you a brief excerpt about what we actually have done, because this gives somehow the reasoning how we came up using GPU-based calculations. And so in the beginning we identified some promising candidates for the studies, and as kind of the benchmark we choose Ordinary Kriging, which is the classical geostatistics approach, and we implemented it by PyKrig, a Python library to implement this. Then we implemented a deep Kriging approach, which is a deep learning module. We implemented this in PyTorch, and as the third model, we just take classic random forest. I think everybody's kind of familiar with random forest, and nothing fancy happened there. We just take the coordinates, the geometry as features, and interpolate or estimate the points we are interested in, and we don't have any data. A little bit more advanced is then the random forest spatial prediction approach, where we essentially used spatial feature which are just distance between points. And this is based on the idea from Hegel et al. I don't know if you heard of him. And we conducted kind of a classical data science approach for these experiments, where we filtered the raw data in the pre-processing step, and we also optimized some hyperparameters for each model itself, and we used Optuna for that. I don't know if you heard of that. It's kind of a nice framework to do so. And then we trained and evaluate the models on a k-fold cross-validation. We can discuss if this is the best approach to do so, but that was the idea by then. The aggregated results gave us a strong candidate, which is the random forest spatial prediction, with the lowest error and the highest coefficient of determination. But just looking at numbers is not so fun. So let's see how this interpolation actually looks on the map. Beforehand, I show you the raw data. So it's kind of not really messy, so it's good. It's high density. We see some overlap areas around here. So we have to clean that. And some missing areas. These are actually boundaries, so quite a good candidate to do the interpolation methods on that. So we choose, on the right hand, we made an interpolation with ordinary Kriging. And yeah, on the left hand, the random forest spatial prediction. And you see that there are a lot of difference between them. So if there are any Kriging enthusiasts here, please forgive me that I don't go into detail about Kriging stuff. It's kind of a deep topic, so I will concentrate on the random forest spatial. We can discuss why this looks like this later. But what we found interesting was like we see some structures here, like lines. And yeah, the question then was, are these some kind of artifacts which were just produced by the random forest spatial because of, you never know? Or are these actually something you see in the data or in the reality? And yeah, thanks to Sebastian, he looked at that and was like, okay, that's probably the tram lines. And tram lines are the paths where the tractor drives to apply fertilizer or pesticides over the year in the crop. And there are actually no crop growing. So this might be the reason. So we gathered the data about the tram lines, got from the GPS, from the application, and plotted them on the on our predicted area here. And as you see, it really looks like that the random forest kind of grasped these tram lines, or this lower yield in the tram lines, and in contrast to the Kriging part. But you might wonder if one could have seen this in the raw data, and so not visualized like that, at least. And yeah, that's why we were quite happy with our results. But this talk isn't about finding tram lines in yield data, but using GPU for this kind of task. Because, as you know, using distance as features and using kind of maybe all distance between all points as features leads to a very vast feature space. So that is really time consuming and time consuming computations. So we found a solution to this issue using rapids. And now I'm going to show you. So yeah, we used rapids besides other frameworks. So normally we made our machine learning in scikit-learn, used Optuna for our hyperparameterization, and now we came up with the rapids. And I want to show you in a Colab notebook how much you have to change, or how little, to make use of GPU computation in random forest regression computing. So I actually wanted to do this live, but I was too afraid that something breaks. So I did this morning, and it runs, so I don't want to click anything now. But yeah, at first, there is a GitHub repo where the code and all the custom code is also stored. We have some installation for the Optuna and for PyKrig for the Ordinary Kriging library, and then for using Rapids in the Colab, you need to install the library via GitHub. If you are on your local machine, which has a GPU, you can make use of. You can just install it with pip or with conda. Okay, here are a lot of imports. We are not using all of them in this notebook, but as you also see here are a lot of custom code which I imported, which I won't show now. And yeah, I just take the data from my Colab drive, and what I want to show you is this. So just for presentation purpose, I just made up programmed these two classes. So this is a CPU-based interpolation class, which make use of the random-forest regressor from sklearn. And as you see here, we have to change the structure of the data to CRS matrix because it's quite sparse, and the sklearn model can't, random forest regressor can't handle this in a normal way, so you have to change it to CRS matrix. Same here for the prediction phase, for the grid where you want to interpolate in, and yeah, that's pretty much all. Everything else is just using the sklearn interface. For the GPU, it actually looks quite the same. There's just one difference. We have to change not into a CRS matrix, but you have to change your data frame into a QDF, which is also just done by QDF.from pandas. So quite convenient. And yeah, then you just do your interpolation. And yes, now you see the numbers already. Up here, the CPU time is about 1,000 seconds. It should be around 80 minutes or something like this. And the GPU interpolation goes through into 40 seconds. So the difference are quite significant. And the nice thing is, yeah, you could probably do it into a neural network and just implement it there and working on the GPU, but from my experience, it's a lot more difficult to explain and to understand what's happening, what is going on. And the random forest is quite easy to explain to a broader audience. So it's nice to use it, and yeah, still can make use of GPU-based computing. This is a really nice thing, and I'm happy to share this with you. So looking at the map, it's a different field than you saw in the slides, but the interpolation looks still the same. So yeah, that's our results. Yeah, and for that I'm finished now.
Okay, thank you for the talk. Are there any questions in the audience?
Thank you. Hello. I just wanted to know a bit more about Rapids and the GPU process. You've shown us on Colab. Do you still need to pre-configure sort of your own machine or hardware with CUDA to access the GPU? So does Rapids do that, or does Rapids use CUDA?
So it's kind of messy using CUDA, using your GPU in Windows, because you have to have an instance of VSS, or you have a Linux instance you need to run actually your computation on the GPU. But if you have set up this, it's just make an environment in Linux where you install CUDA, and then you can just make this script like this, not like a notebook. So I just use it for demonstration purposes as a notebook, and then run it in Colab because GPU is here available. And then you can just run your script and use Rapids as you use sklearn on CPU. So it's quite convenient, yeah. But the first step, setting all this up on the Windows, is quite tedious, yes.
Thank you very much for the presentation, and I'm wondering, have you assessed the cost efficiency? So, for example, if you run on CPU or GPU? No.
No. We just wanted to use the best model, and in some reasonable time. And I did all the experiments on this machine. It was there, so of course, looking on for this Google Colab, I paid 11 euros. So I have it available now, but we have no other figures for that. Yeah.
I have one question. Have you tried to validate your interpolated data with some field measurements?
So, I mean, these numbers here are more like a split. So we take just 70% of the data for training and 30 for testing. And yeah, we didn't. So that's historical data, and we didn't went out on the field and collected these 10 or these 100 square meters and looked if our interpolation is something good. It's kind of a problem to have real values for interpolation tasks. That's true.
Okay, thanks. More questions? Oh, 3 more questions. Nice.
Thanks, and a really nice presentation. I was just curious, this leads to advice to farmers on which eco-scheme they should apply for. I was wondering, is this advice on a parcel level, or do you also look at specific sites within a parcel and advise on that? Because it looks like these results are for the entire parcel. Yeah, I was just wondering if you extract sites inside the parcel to give advice on or not.
Yeah, so it's site-specific, yeah. Within the field, subplots within a field, yeah.
But can the farmer then apply to an eco-scheme with a subsection of a parcel? Oh,
Yep.
okay, I didn't know.
So there are some regulations, but they are pretty slim. So I think it's like at least 100 square meter per eco-scheme. So it's pretty flexible, yeah.
Okay, thanks.
Thanks for your presentation. I was wondering about like the next steps. You mentioned it's a POC right now, and it was somewhat successful, right? And is this software then commercialized, or are farmers free to upload their data and see it or see their yields?
So at the moment,
Thanks.
So first of all, it's open source. So we did that work at the university in a funded project. So it's open source, and yeah, at the moment it's only available to us. So the web app is only available to us because it's not a final product now. So we only looked at the yield and made our economic calculation based on yield and assumed everything else to be static for the field. So in real life, we have some cost positions, expenses that are also need to be considered site-specific. And that is one step we want to take next, let's say. So to get a real good recommendation for the farmer, we need to do some more work.
Yeah, sounds cool. Maybe also for nitrogen value interpolation or something would be quite useful for farmers, I guess.
Yeah.
Thanks.
One more question? Okay, then I would say thank you, Lukas and Sebastian, for your talk.
Thank you.